Hey friends, it's Ben again. This is a video for the Calc 1 class on, what is it, the 17th of November. We had some stuff that we didn't get time to do in class. And so I'm making a quick video where I've got my iPad in hand and a calculator in hand, since I can't ask y'all to do the calculations for me now. But what I'm going to do on these is essentially just work out some examples. And what I would like to suggest for y'all to do is, before I start, you try it and then, come back and see what I did on things, right? And if it's something where you started and you got stuck, if you could follow along with what I was doing until you get to your stuck point, and then pause again and so forth. Okay, just kind of strategic things. The more you can do, the better you will be prepared to do this in the future. Okay. All right, so I'm going to share screen yet again and put the iPad up on here. Okay, so this particular problem we skipped over in class. I wanted to suggest to you all to go ahead and try this, but the notion of what we're trying to do is to get a relative error here. Okay, so we're going to get an estimation on the worst our error could be, and then divide by what the reading is that we have, so that we have an idea of what percentage your error could be in, right? And this problem also has to do with an idea that we call, if I can spell, propagation of error. Okay, which is to say, when you make a measurement and then use that measurement to approximate something, because there might be an error in your measurement, that would mean that, clearly the calculation is going to have some error as well. And we're looking at how much that error can be affected. Okay. So if you take a look here, notice that we've got this radius of the Earth being measured at 6,400 kilometers, but plus or minus 550. That means that the error could be anywhere from, being zero error, perfect, to an undermeasure or an overmeasure of as much as 550 kilometers. How they got those, I don't really know. But if you wanted to talk about the relative error for the R, then you would take the 550 and divide it by this 6,400. And because y'all have met me, you know that I can't do that in my head. But when I do that, I'm getting like 0.0859. So if somebody asked, I might say that I have an 8.6% relative error. Okay. So now we're going to look at doing the same sort of thing with the linear approximation on the, the volume that we're getting for the Earth. Okay. So you have to know the formula. Volume equals 4/3 pi r cubed. And before anybody says anything, I will go ahead and say, yes, I know the Earth is not a perfect sphere, but it's close enough. Okay, we can get a fair approximation. And if you wanted to use some other formula, well, yeah, good luck with it, I guess. So what we're going to think about here is getting our change in V by doing that dV idea. And so we'll have to take the derivative of our formula. So when we do that, the 4/3 pi r cubed, the derivative of the r cubed will be 3r squared. And then after that, we will put the delta r. The delta r is going to be the possible error. Okay. So we can cancel the 3's there. And then we're dealing with 4 pi times the r squared. And the r we have in mind is the 6400. And then times the delta r, which is going to be this plus or minus 550. Don't worry about the plus or minus. You can just put that on at the end, because up here at this point, I didn't say plus or minus 8.6%. I just said it was an 8.6% relative error. Okay. All right. So the number that we get there is going to be entirely huge. So the thing I would do is to just go ahead and get that number and save it in my calculator. Now, since y'all can't see my calculator screen, I will go ahead and put the number that I'm getting here out of it. But I want you to bear in mind that I'm just going to put it into a variable in my calculator and not worry about it. So the number that I got there went into scientific notation, and it's like 2.831 times 10 to the 11th power. Okay. So let's see, billions are the 9th power. So that's hundreds of billions of cubic kilometers. But if we just calculated the volume with that 6400 there, and did that on the calculator, 4 pi times 6400 to the 3rd power, I would be getting 3.294 times 10 to the 12th. So considerably bigger, you know. And then dumbly enough, when I said something earlier about that I was going to store something, I didn't store it. So I will have to go back and do that real quick. And then I will also store the v there. Makes sense to maybe store it under the variable v, except I can't type variable v. Yeah. Okay, and so I'm just going to go ahead and get my relative error for the volume. And I'm going to take that 2.831 times 10 to the 11th. I'm going to divide it by this 3.294 times 10 to the 12th. And I've got them both stored in my calculator, so I don't have to type them again. But I do have to find the button. All right. When I did that, I got 0.859. So I got the exact same relative error. Well, that's weird. I did not think that that would happen. There's probably a reason behind it, but really what we're looking for here is the mechanical portion of what we're doing. And we're getting that. Oh, that was really ugly. Sorry. We're doing the the linear approximation and then dividing it by that total volume. So, all right. Hopefully you all feel good with that. And we did several of these problems in class, but now we've got a couple, 3 more. Let's see, 1, 2, 3 that we're going to try to take a look at. So the first one here on this absolute extrema says we've got our r of x being x over x squared plus 1 on the 0 to 2 pi. So the stuff we're doing, we're going to find r prime of x. And of course, that means we have to use the quotient rule. And the quotient rule, I will write over here to the side, u over v equals u prime v minus u v prime, all divided by v squared. Okay. So a derivative of x is just 1 times the x squared plus 1. minus, I have x times the derivative of x squared plus 1 is just 2x. Divide all that by x squared plus 1 quantity squared. And let's simplify it just a little bit. We'll end up with minus x squared plus 1 over x squared plus 1, the quantity squared. Now, the denominator cannot be 0 because that x squared is always greater than or equal to 0. And when you add 1, you get something that's greater than or equal to 1. So no critical points coming out of the denominator. So our critical points have to come from setting the numerator equal to 0. And that tells us that the x, I shouldn't write that there. It tells us that the x is going to be plus or minus 1, right? And then, of course, we also have the endpoints that we put in our list. So I'll say x equals 1, x equals minus 1, x equals 0, and x equals 2. All right. So when you were doing this, hopefully you spotted this is not my interval. So I'm going to go ahead and throw that out. So we only have to concern ourselves with stuff that is in the actual interval. But you will check R of 1, R of 0, and R of 2, and see what you end up with on those. My 0 looks too messy. All right. So for R of 1, we're just plugging into the original, and you'll have 1 over 1 squared plus 1, so you just get 1/2. Okay. And then the R of 0 will end up being 0, and the R of 2 will be 2/5. And if it would help to do decimal approximations, go ahead and look at those, and you would see that this is 0.5, whereas this one is 0.4. So your maximum value is coming out of the critical point, and your minimum value, that is a badly drawn rectangle, but your minimum value, it's still a badly drawn rectangle. If I try it again, maybe it'll be better. Yeah, all right. Your minimum value turns out to be 0 there. So hopefully that makes sense. And that's the kind of thing that we're doing in all these problems, is looking for critical points and then just plugging stuff into the function. So here, we're looking for absolute extrema of log x divided by x. So we learned relatively recently that when you take log x and take its derivative, that you get 1 over x, okay? And because we have a quotient rule, we'll also need to have that. Yeah, my prime is probably not very visible there. So, all right, but go ahead and try this and then come back. Okay, so you've just unpaused, and we will find out for our S prime, we need to do the quotient rule, and we'll say the derivative of the top, log x, is just 1 over x times the bottom minus log x. I'm going to put parentheses around it so we don't try to suck other things in here, but then times the derivative of the bottom is just 1, and now we square the bottom. So you get a little bit of cancellation going on, and then you also have that 1 there. So this turns into 1 minus log x divided by x squared. So when you're looking for critical points, you would think about making this undefined at x equals 0. But if you look back at the original function, we also could not put 0 into it. And the interval we have doesn't even include the 0. So that is something that you don't really need to note, but I did. So I'm going to take this 1 minus log x over x squared and set it equal to 0. And we remember that if you've got a fraction and it's 0, it had to be the top that made it 0. And that means that log x has to be 1. If you exponentiate on both sides, you will get e to the log x is just x, and e to the 1 is just e. Then you have to check and see, is e in this interval from 1 to 3? You might have to check to see about this, but e is about 2.7. So yeah, it's somewhere between 1 and 3. So we're going to go ahead and use that. And so our list that we have to think about what to check is going to be x equals e, x equals 1, and x equals 3. So we're just going to plug them in. And so s of e, s of 1, and s of 3. Okay, so when I plug in to the ln of x, the top is a 1, and then that bottom of e, and I am going to get an approximation for that of about 0.368. Okay, you can be more exact if you want, but please bear in mind all these approximations are not exact numbers. 1 over e is the exact solution, and you don't have to do any more. But we need to compare numbers, so we'll want to do that. All right, when you plug in the 1 to the log x, the log of 1 is 0, and then divided by 1, so we get 0 out of that. And when you plug in log 3 divided by 3, I don't know what that will be, so I will ask my calculator, and it says that that is about 0.366. Oh man, look at that. This one turns out to be the max, but it's super close, right? And then this one turns out to be the minimum. And that's what we're looking for, all right? Cool. All right, so on this one here, we're looking for absolute extrema. The function is x squared e to the x from -3 to 1. So go ahead and pause and try that and then come back. All right, you're back. So hopefully the way you started was getting u prime of x. And of course, that's a product rule. So you have 2x times e to the x. We took the derivative of the x squared, but left the e to the x alone. Plus, now we leave the x squared alone and take the derivative of the e to the x. So it might be handy to factor that like so. Now, you look at the function. There's nothing that will make it undefined. So we set it equal to 0. When is e to the x equal to 0? The answer is no, it's not. It's never equal to 0. So you don't have anything coming out of that. So we really need to think about the other factor here. And so I'm going to take and factor that into 2 plus x and x. If you want to write the e to the x down, you can, but it's not going to be 0. And this says that either my x is -2 or my x is 2. Both of those, oh, I started to say both of those were in my interval, but no, turns out x equals 2 is too large. So I end up having to eliminate that one. So my list is just going to be x equals -2, x equals -3, and x equals 1. Okay. We threw out the x equals 2 because it's not between -3 and 1. So, okay. And if you're saying, hey, Ben, did you just do something stupid? You would be correct. Man, if I were a little bit more ego invested in this, I would go back and erase that. I used the x equals 0, didn't I? Okay. All right, sorry about that. But now we are just going to have to evaluate u of -2, u of -3, u of +1, and u of 0. So for the -2, you'll get 4 times e to the -2. I'm going to need an approximation for that. So I turn to my calculator and I get about 0.541. Okay. And then the -3, I will end up with a 9 e to the -3. So 9 e to the -3, I'm getting about 0.448. For the u of 1, I'm going to get 1 times e to the 1, and that's about 2.718. And when I plug in the 0, the x squared there is going to make it 0. So notice all of those were positive, and thus it's all the others were positive. So it's very easy to pick out which one's the minimum. And then the maximum is way larger than the other values. So it's also easy to pick out. And I forgot to write the word max beside it. Anyway, all right, good. All right, one more here. And this one, of course, has trig functions. Right? So let's see what we can do. Oh, wait, pause, and you try it. And now we're back. And so I'm sure you started with v prime. And you said then that's 3 times cosine x minus 2 times. Now you have to spot that the sine cubed x is the sine of x and then cube. So when you take the derivative of a cube, you would have 3x squared. But instead of the x being squared, you'll write sine x being squared. And then the chain rule says that the derivative of sine needs to go there as well, and that's just cosine. Okay. Now, it would be super convenient on this if we went ahead and factored things. Y'all can spot, I hope, that a 3 cosine x will factor out of the whole thing. And then you'd have a 1 left from the first term minus a 2 sine squared x. Right? Now, when you look at this, you'll spot that there's no division by 0, so no critical points from that way of doing things. So we will instead set it equal to 0. Now, 3 can't be 0, but cosine can be 0. And in class today, Riley made this point that it's going to be odd multiples of pi over 2. And we're going between 0 and pi, so we'll actually only get pi over 2. If this had gone 0 to 2 pi, we'd also get 3 pi over 2. Okay, but this was cut off to be like that. So then the other piece, when we say 1 minus 2 sine squared x equals 0, that means the sine squared x has to be 1/2. So the sine x is plus or minus 1 over the square root of 2. And you'll remember that that has to do with reference angles of pi over 4. And that means for our purposes, we'll get pi over 4 and 3 pi over 4. If it had said 0 to 2 pi, then we would also pick up 5 pi over 4 and 7 pi over 4. This one was cut off there. So I formulate my list. X equals pi over 2, x equals pi over 4, x equals 3 pi over 4, and then x equals 0 and x equals pi, because the endpoints can end up having maximums or minimums on them. If you remember that example we had with the x times the square root of 4 minus x squared, you can just end up having a maximum happening in an endpoint. And plenty of these absolute extrema have had that happen. But this is a pain because there are so many to evaluate. But the best way to get them done is to start. So I'm just going to make my list. I will not, however, check it twice, despite the fact that my round little belly shakes like a bowl full of jelly. But we're going to run through and just evaluate. And remember, we are not evaluating the derivative, but rather the original function. Okay. And this may be a little bit of a hassle because it's kind of an involved function, right? So I think I'm going to grab these and pull them over there to make more room. All right, so 3 times the sine of pi over 2 is 1, minus 2 times the sine of pi over 2 is still 1. So we'll end up with 3 minus 2 is 1, okay? Then the next one, 3 times 1 over root 2 minus 2 times, when you cube that, you'll have 1 over 2 root 2. So that's 3, 6, yeah. I forgot to cancel. That'll make this a little bit easier. So you'll have 3 minus 1 is 2 over root 2. So it simplifies as just root 2, okay? That's about 1.4. And then for 3 pi over 2, you'll have 3 times the negative 1 over root 2 minus 2 times, and you'll end up being a negative 1 over 2 root 2, so kind of like before. And you'll again do a little cancellation, but this time you'll get negative square root of 2, so about negative 1.4. Then plugging in 0, sine of 0 is 0, so we just get 0. And the same thing for pi, okay? So when we look back at this, we will see that our minimum happened here for the negative root 2, and our maximum happened here for the positive root 2. I'm going to separate things a little bit better so that when I circle the middle, look like I planned it. Okay, so that is the kind of thing that we're looking to do on these. And sometimes it gets a little bit yucky because you have to check a whole bunch of points on it, but at least you're not having to come up with points. And you're not having to plug back into the derivative, you're plugging back into the original function, okay? So that's what we do on those. All right. Thank you. I will see you in class on Friday.